In this activity, we're going to go ahead and create confidence intervals using Hershey's Kisses and try to estimate what proportion land flat. Now, on some of these, this is done with the class, and so I have answers will vary at times, okay? So I'll try and clarify the best I can. When you toss a Hershey's Kiss, it sometimes lands flat and sometimes lands on its side. What proportion of tosses will land flat? So we have each table basically had Hershey's Kisses and had 50 rolls, and we're trying to estimate what proportion landed flat. The answers varied. We had, I think the lowest we had was below 0.20, and the highest we had was actually above 50%. So each table put their point estimate. So the point estimate is from your sample, and it's a p hat. So that's one of the hard parts of the inference sections, is we have symbols for things that look similar, and they're for similar things, but they're not for the same things. So point estimates will have this little hat on top. So the population is all Hershey's Kisses, and we had 50 rolls of Hershey's Kisses. P is the true proportion that land flat, and p hat is from the sample from each table. So was a sample a random sample? I sent the students to go get Hershey's Kisses from the bags. So I would say not really, but we're confident that our bags of Hershey's Kisses are representative, so there's no reason to think that one sample is super unusual, other than just unlucky chance. All right. So what was the formula for calculating? Oh, let me add a little hat here. There we go. The standard deviation of the sampling distribution of p hat. Well, it's sigma p hat is equal to p times 1 minus p over n. That's where p, and let me go ahead and add that little note, where p is the true proportion. All right. Now, but in this instance, we don't know the true proportion. All right. So what condition must be met to use this formula? It's a 10% condition, because we want to make sure that P is not changing. All right, so let me go ahead and add that in. We want to make sure that P is not changing. All right, so that allows us to use the formula. But the problem is we don't know P, so we're going to use P hat, and that changes the name. It becomes standard error of p hat instead of the standard deviation of the population, all right? Or for the sampling distribution, I should say. So anyways, now we have our p hat times 1 minus p hat over n, and we calculate with p hat from your sample, and n is 50. And the answers are going to vary. Actually, I'll go ahead and come down here to this picture right here. Well, let me zoom in just a touch. We can do that. So you can see these are some of the standard error calculations we had for the different tables, all right? And they were basically taking, like this one was 0.34, so they would put in 0.34 times 1 minus 0.34 divided by the 50, and that gave them 0.0670, okay? So that's how we calculated the standard error, and then the question is, could we use a normal distribution? So for shape, we're trying to avoid skew, and that means that n times p, we need at least 10 successes and at least 10 failures. And for all of our values, at least on this particular class, all our values for p were fairly large. I think our lowest was 0.26, our highest was 0.42. We were doing 50 rolls, so we were getting at least 10 for each one of those. Now, in order to create our confidence interval, one of the things we have to do is determine our critical value. So that's an important value right here, the critical value. So we could use table A. You do get table A when you take the AP exam, and it's available in my room. It's the yellow thing. It'll be white on the AP exam. But you can actually just use technology. So if you're using your calculator, just make sure that you use Z star. Z star stands for critical value, all right? If you're doing Z, it's a Z score, but Z star is critical value. They should be very similar to the empirical rule. The empirical rule says 95% of data lies within 2 standard deviations. But if we do it with technology, we see it's not exactly 2, it's 1.96. You should totally memorize some of these. Oops, I don't need that. So some of these memorize, I would memorize 95% and 90% and probably 99%. Now remember, you can write these on your cheat cards for your tests. They're not hard to find as long as you put in the area in the center. So that area right there is your confidence level. And then your mean is 0 and your standard deviation is 1 because these are related to z-scores. It's standardized. Okay, so then we calculate the margin of error. So what we did is we take the critical value and we multiply it by the standard deviation. So if you look at my little image here, margin of error is your critical value times the standard error, all right? And so these are the things that say ME here. These are the different standard errors. Some of these match, so I didn't bother rewriting them. These were all 0.122. And so we started our point value for the confidence interval. Then we go up and down by the standard error. Here we go up and down by 0.131. So I can rewrite this interval as 0.34 plus or minus 0.131. Or I can just go ahead and find the lower bound and the upper bound and write it in this format right here. So there are multiple ways to write your intervals, either in this format or this format over here. Now, you should be able to get from this format to the other, so you should be able to switch. If I gave you 0.209 to 0.471, how can you get 0.34? Well, hopefully, what you would do is you would add these two things together and divide by 2 because it should be the average or the midpoint. And then you could just subtract these two values to get your margin of error. So the margin of error is the width on either side of our point estimate. All right, and then finally, these are all of our confidence intervals that we generated in this class. And P equals 0.35 is, as far as we know, the true value based on the many times we've done this. The proportion of Hershey's Kisses at lamb flat is 0.35. In this class and in most of my classes, everyone happened to capture the interval. But even if you didn't capture the interval, that doesn't mean you did anything wrong, okay? It's kind of like standard error. Standard error sounds like it must be a mistake because it has the word error. Now, that's just the random variability that is part of this whole process, okay? So when you hear the word error, that's not always a bad thing, okay? So we did have some intervals that didn't capture it, but it's not because the students did anything wrong. They just had an unlucky toss, and that happens every once in a while. And then remember that the whole process of the interval is we're 95% confident that our method, when done correctly, will capture the true value. All right, the true value doesn't change. I don't change this 0.35 from year to year. It's always 0.35. What changes are the intervals and then also whether they capture it or not. And where the confidence level has to do with the process, it's not about probability. And so that's a quick walkthrough of the creating a confidence interval for proportions. Oh, and then we also did a check for understanding here. What do you want to be when you grow up? According to a nationwide survey of a random sample of 1,000 kids under the age of 12, some kids want to be a ninja, a dragon keeper, a dancing unicorn, and even an octopus. That's kind of cool. 55 of the 1,000 kids want to be a doctor. We would like to use this study to find a 98% confidence interval for the true proportion of kids who want to be a doctor. So identify the parameter of interest. P, not with a hat, is the true proportion of kids who want to be a doctor. All right. Now, P hat, oops, I'm forgetting I have to add the hats as a little mark at the end. So sometimes they get left off on these camis, and it's not on purpose, I promise you. So P hat in this case, that's P hat right there. Okay. So why am I using P hat instead of P? Because I don't know what P is. So I have to use something to stand in, right? So P hat is this 55 divided by 1,000. So we're going to check the conditions to see if we can construct a confidence interval. 1,000 kids is less than 10% of all kids nationwide. It says random sample. Let me go get it. says random sample of, where it is, there we go, a random sample right there. It tells you it's a random sample, so we're good. And then we check our successes and failures. Our successes are 55. Technically, I didn't have to calculate this because it was given there. And I could have just said 1,000 minus 55 to get the 945. So all conditions are met. Then we find the critical value for a 98% confidence level and then calculate the interval. Oh, excuse me. My computer's being wonky. And you can see here, so my critical value is 2.33. So how did we calculate that? Well, that was back here. So you might want to highlight. Let me go ahead and highlight this puppy. Might highlight it kind of this formula right here. And I know I just sort of covered it up. That formula right there, that is the formula to calculate a critical value. Just don't use 0.8 every time. Use whatever your confidence level is. So I would use 0.99 and I would get 2.576. So here, this one was 98%. I don't think we had a 98% in here. We did not, but I can tell you it is about 2.33. And then we calculated our standard error. We just multiply the critical value times the standard error to get the margin of error. And then our confidence interval is our point estimate plus or minus our margin of error. And you can actually calculate the lower and the upper bounds, which it's nice to have these because it's easier to interpret when we have those. So we say we are 98% confident that the interval from 0.382 to 0.0718 captures the true proportion of kids under 12 nationwide who want to be doctors. And that's it for that example.